This video gives a detailed description of an early aircraft engine, the Gnome 9-cylinder single-valve or monosoupape engine, monosoupape being French for single valve. It was developed in 1913 and powered quite a few aircraft during the First World War. Although it's a French engine, it was mainly used in British aircraft, including the legendary Sopwith Camel. It's pretty amazing to think the Wright brothers made the first powered flight only 10 years earlier with an innovative but far simpler engine, which I've described in another video. Before I describe the technical details, I'll spend a couple of minutes giving some general information and background on the project. In a rotary engine, the propeller is attached to the cylinders which rotate around the stationary crankshaft. This is in contrast to a radial engine, where the crankshaft rotates and the cylinders stay still. The flow of fuel into the engine was continuous. The pilot adjusted the flow manually by means of a valve and made frequent power adjustments by using a blip switch which turned off the ignition whilst it was pressed. The rotating cylinders act as a flywheel, keeping the engine rotating, but with the penalty of a large gyroscopic torque, which makes left turns easy and right turns difficult. It was said that if you wanted to turn right, it was easier to make a 270-degree left turn, but that seems to be a joke rather than fact. Cooling was a major problem, and the rotation also helps with that, particularly when the engine is on the ground. But there is no practical way of fitting an exhaust pipe to the rotating cylinders, and together with the total loss oil system, the pilot was covered with a mix of toxic gases and castor oil. The pilots wore long scarves to wipe the oil off their goggles, not to look cool. Castor oil was used because it doesn't dissolve in petrol, but castor oil is a powerful laxative, and that gave the pilots additional problems. The project was mainly about learning 3D graphics. My main resource was this maintenance manual, rather than detailed plans. This is the only real plan, and I spent a lot of time figuring out how it worked. There were some photographs of the disassembly and of individual parts. This is where I got the manual. I created the model in a 3D software package called Blender. It's a great package and totally free, although you can and possibly should make a donation to the Blender Foundation to help keep it going. There are a few of these engines in various museums around the world. I found one in the fantastic Swiss Transport Museum in Lucerne, one of my favorite cities. This is the 7-cylinder version. The cylinders and valve gear are interchangeable with the 9-cylinder version. If I'd known that before I started, I'd have modeled this version and saved myself a lot of work. There are also 11 and 18-cylinder versions. This is a radial engine. As you can see, the propeller attaches to the crankshaft rather than to the cylinders. It's not a Gnome and Rhone, of course. I can't recall the make. Apart from the incredible section on aviation and space, there is an equally incredible selection of cars stored in a multi-level display. At the press of a button, a mechanical lift will swap cars around and fetch any of the cars for you to have a closer look at. The museum covers all forms of transport, including trains, ski lifts and watercraft. The trains are particularly impressive. Lucerne is my favourite place. Now for a more detailed description. Let's start by looking at how the 4-stroke cycle works in this engine. I've created this schematic model to show this more clearly. Air is collected by scoops on the body of the aircraft and flows continuously into the crankcase through the hollow crankshaft. A nozzle at the entrance to the crankcase entrains fuel into the air, thus creating a rich fuel-air mix in the crankcase. This mix is too rich to ignite. There is a ring of holes low down in the cylinder walls. When the piston is near the bottom of its stroke, this rich fuel-air mix can be sucked into the cylinder through these holes. Now let's look at each part of the cycle in detail. During the induction stroke, the piston descends, the valve is open, and fresh air is sucked in through the valve. Just before the piston uncovers the holes in the cylinder walls, the valve closes and the rich air-fuel mix is sucked in from the crankcase. During the compression stroke, the fresh air dilutes the rich fuel air mix to make the correct mixture. About 15 degrees before top dead center, the spark plug fires and ignites this mixture, pushing the piston down and generating power. The valve opens before the piston reaches the holes in the cylinder wall, so that when the holes are uncovered, the pressure in the cylinder and in the crankcase are roughly the same. Thus, exhaust gases don't enter the crankcase and fuel air mix doesn't enter the cylinder. Notice that there is a fairly narrow annulus between the crankcase and the holes, which will help prevent mixing. The piston ascends, forcing out the exhaust gases. This is followed by the induction stroke. The cycle is complete. Now let's look at the actual construction. The crankshaft carries the weight of the engine and all the other forces associated with the engine in flight. It is attached to the aircraft by a taper joint at the firewall and another connection further aft. The crankcase, cam housing and the propeller assembly are mounted on the crankshaft by 4 roller bearings spaced along its length. The crankshaft is in 2 parts for assembly purposes. The 2 parts are connected by a taper joint with a rectangular key. The rear part is a hollow tube. Air from the scoops on the aircraft flows through this tube and into the crankcase. The positioning of this scoop or scoops depends on the aircraft. Fuel is entrained into the airstream by a nozzle mounted at the entrance to the crankcase. There are 3 connectors on the crankshaft, 1 for fuel and 2 for lubricating oil. These are connected to pipes inside the crankshaft. The lubricating oil travels through various passages in the engine until finally passing into the crankcase and leaves with the exhaust gases. I'll mention the oil system more when we get to the various parts. Both the oil and the fuel can be gravity fed from their tanks, or the tank can be pressurized. The oil is then pumped into the engine. The oil pump is mounted on the firewall and driven from a gear attached to the rear of the crankcase. If the tanks are pressurized, an air pump is also fitted in the same way. I didn't model these pumps, but here are the diagrams from the manual. Now the connecting rods and pistons. There is 1 master connecting rod, and there are 8 normal connecting rods, shown with the pistons attached. Notice the small pipe attached to the side of the connecting rod. This carries lubricating oil to the pairing at the piston end, known as the gudgeon pin. 2 ball bearings allow the master rod to rotate around the crank pin. The crankshaft must be split to mount the master rod. The master rod includes 8 pins on which the remaining connecting rods are mounted. These rods are free to rotate around these pins. Normally, of course, all the pistons would be fitted before putting the master rod on the crankshaft. The master rod acts in the same way as a connecting rod in a conventional engine. As the engine rotates, the eccentricity of the crank causes the piston to move up and down the cylinder. The other 8 connecting rods are mounted on the pins because they need some freedom of rotation because they change their angle relative to their cylinder as the engine rotates. The valves are a fairly conventional pushrod design. The pushrod rocks the rocker, which opens the valve spring closes the valve and returns the pushrod to its rest position. The rockers are designed so that the centrifugal force is equal on both sides and doesn't try to either open or close the valves. This video shows the assembly. The spring is attached to the valve stem by a pair of retainers known as cotters, which are held in position by the cup. The valves are controlled by cams. Let's look again at the simplified model. As the cam rotates, the valve opens and closes. A cam follower lifts the pushrod, which opens the valve. A ball joint between the cam follower and pushrod accommodates the changing angle. The roller, a small wheel on the cam follower, reduces friction. This is a 4-stroke engine, and so it takes 2 full rotations to complete 1 cycle. The cam must therefore run at half the engine speed, 1 rotation of the cam for every 2 rotations of the engine. In a rotary engine, the cylinders fire alternately 1, 3, 5, 7, 9, 2, 4, 6, 8, etc. This is why rotary engines always have an odd number of cylinders. The 18-cylinder engine has 2 banks of 9. This is the timing diagram for the engine. To interpret it, start from point A and follow the spiral anti-clockwise for 2 rotations. The 9 cams, one for each cylinder, are mounted on a cam block which is mounted on the front part of the crankshaft and rotates around it using a sleeve bearing. The sleeve bearing is lubricated by oil which has flowed through the galleries in the crankshaft. This oil flows through holes in the sleeve, along the channels formed by the grooves in the sides of the cams, and into the crankcase. The cams must rotate at half the speed of the engine. A fixed gear on the crankshaft engages with a pair of compound gears bolted to the camshaft housing. The smaller gear in each compound gear has half the number of teeth of the larger one, and this smaller gear rotates the gear fixed to the cam block. And finally, the ignition system. A magneto, which isn't modelled, mounted on the firewall and driven by the same gear that operates the oil and air pump, generates the high tension voltage. This is connected to a distributor by a spring-loaded brush shown in the planned close-up. The distributor supplies current to each spark plug at the appropriate time in the cycle through a bare wire. That's the end of this video. I hope that you enjoyed it and that it added to your appreciation of these incredible machines and the people who designed, built, maintained and flew them.